Besides base 2, another number base that's useful when dealing with computer data is base 16, and there's a good reason for that. Numbers in base 2 are kind of hard to keep track of because even small numbers are fairly long and only 2 digits are ever used. We're going to take a simple number here, 1100, and I'm going to group these in groups of 4. So each one will take up half a byte, 1010 and 1101 and 0001. So these two would take up 1 byte, these two would take up 1 byte. So we've got some data here that represents 2 bytes. We've got 16 bits there. If you want to copy that number, it's real easy to make a mistake when you're doing it. And so what we do instead is we convert these numbers to base 16. Okay. Now, a number base tells you 2 things. If I have base 16, that tells me that I have place values that are based on powers of 16. So 16 to some power. You know, in the first rightmost column would be 16 to the 0 power, which would be 1s. In the next column would be 16 to the 1s column, or 1s power, which would be the 16s column. And in the next column would be 16 to the 2nd power, which would be 256. And after that, I'm not sure I can do that in my head, so we'll stop there. So that's how base 16 works as far as place values are concerned. The other thing that a number base tells you is how many digits there are. So in base 2, there are only 2 digits, 0 and 1. In base 10, there are 10 digits, 0 through 9. And in base 16, there are 16 digits. Well, we've got a problem because once we go from 0 up to 9, then we're out of digits. Those are the only digits that we normally use. So we have to make up some. So for the number 10, we're going to use the letter A. For the number 11, we're going to use the letter B. For the number 12, we're going to use the letter C. For the number 13, we're going to use the letter D. For 14, we're going to use the letter E. And for 15, we're going to use the letter F. That takes a little bit of getting used to, thinking of letters as representing numbers, but that's what you have to do if you need more than 10 digits. So the number 0, and then we're going to, it turns out that each one of these can be represented as a 4-bit binary number. 0 is just going to be 4 zeros, and you know what the rest are up to 9, so 9 is 8 plus 1. And then the letter A is number 10, which is going to be 1010. B is going to be 11, which is 1011. C is going to be 12, which is 1100. D is going to be 13, which is 1101. E is going to be 14, which is 1110. And F is going to be 15, which is 1111. And that is the biggest possible 4-bit number. So we've covered every possible combination of 4 bits, from all zeros on the low end to all 1s on the high end. Okay, so we can take any number in base 2 and divide that number up into 4-bit chunks and assign each one of those a hex digit, hexadecimal digit, or hex for short. So that is the number 12, and we see that the number 12 here is going to be represented as a C in base 16. That's the number 10, and that's going to be a letter A in base 16. That is the number 13, and that is going to be the letter D in base 16, and that's the number 1, which is just going to be the number 1 in base 16. So this number right here is CAD1 in base 16, whereas it is that 16-digit number in base 2. And there are 2 advantages of doing this. One is that it's much shorter. The other is you're much less likely to make a mistake copying this number than you are copying this humongous number over here. So most of the time when you're looking at binary data, you are probably going to be looking at it not in base 2, but in base 16. And if you need to convert into binary, it's real easy to do that. Just reverse the process, going from our base 16 digits over to our 4-digit binary number.